Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired operating systems engineer going back to the MS-DOS and Windows 95 days. And today, we're continuing our journey back to explore the very fundamentals of computing by looking at questions such as how does the CPU read a byte from memory and how does it communicate with its own I/O chips? In each episode, we'll take a look at a new aspect of this 1977 KIM-1 system so that by the end, you'll be familiar with all the components that are essential to the operation of a simple desktop computer. Our mission today is not only to communicate with the KIM-1 for perhaps the first time in 45 years, but also to learn how it actually does basic input and output without a screen or keyboard. That I/O is performed by a pair of chips with perhaps the coolest name in the pantheon of integrated circuits, the Riot chips. And the bigger problem is that the chip that should be handling my serial I/O isn't working. We'll fix that today as well once we figure out what's actually wrong with the board. The KIM-1 was originally designed to operate with a paper printer and keyboard like this ASR Model 33 teletype. Before video terminals were commonplace, the teletype was the preferred method of input and output, and it's how folks like Bill Gates and Paul Allen interacted with the time-sharing systems that they both initially learned on at the Lakeside School in Seattle. It's also what they later used to develop the basic software for the Altair and beyond. In those days, a serial terminal cost more than the KIM-1 itself, and my oldest terminal is this video-based VT220, so we're actually going to replace the ancient teletype with a standard RS-232 serial connection. Now, a fun fact about the ASR33 teletype is that it also had a paper tape punch and reader attached. When enabled, any letter or number that you entered on the keyboard was printed on the page as normal, but also encoded in binary as a series of holes across a row on the tape. Anything that the computer sent down to the terminal could similarly be encoded onto the tape. But that's only interesting when you realize that you can play the tape back later. Let's say you enter a simple basic program with the teletype. To create a paper tape recording of it, you could have recorded it while you were typing, or then simply type list and then turn on the paper tape punch. Your program will be recorded onto the tape. And you can play that tape back later and it will dutifully enter your program just as if you had typed it all back in manually, but of course, much faster than typing. Data is encoded on a paper tape using a series of punched holes known as Baudot code, and it dates back to the telegraphy days of the 1870s. Each character is represented by 5 bits. Now, if you're Monsieur Baudot back in the 19th century inventing this code, you have to decide how to encode each letter. So do you code them in alphabetical order or frequency order? Baudot appears to have largely used inverse frequency, so that the most common letters had the fewest holes. E and T get 1 hole each, and the other common letters from the Itow and Sherdlu mnemonic get 2. Now, if you've never encountered Itow and Sherdlu before, it's a nonsense name that helps one to remember the most common 12 letters in the alphabet by frequency. Memorize it now, and you can thank me later if you're ever on Jeopardy! Itow and Sherdlu. I've long assumed that Baudot's strategy was intended to place the least wear and tear on the machine, since it punches the fewest holes, but the goal might also have been stronger tapes, as giving the most common characters the fewest holes would naturally reduce the number of overall holes punched into the tape. More holes would have produced a weaker tape. The KIM-1 can also read and write binary data to and from the paper tape, so you can save a range of memory out to tape and load a program back from tape as well. You can do this from within the KIM's machine language monitor. Now that monitor is super limited. All it can really do is display a byte of memory, replace a byte, and load and save a range of memory addresses. That's it. No debugging. It's extensible, but it starts out very bare bones. We're going to simulate the paper tape with a standard serial console, and by the time I'm done today, clicking Build in Visual Studio will compile and assemble the code, link it into a binary, and code that binary into a paper tape file that can then be fed directly into the KIM's loader mechanism over the serial port. As noted earlier, the KIM-1 communicates with the outside world via a pair of Riot chips. They ultimately give the KIM-1 its name, for it stands for Keyboard Input Monitor. Riot stands for RAM, I/O, and Timer, and each chip incorporates all 3. Now actually, the 6530s in the KIM contain both RAM and ROM, so they're actually best called Riot chips. Roll that R. Thus, the 6530 is really a bunch of chips combined, or more precisely, all of the features from several chips packed into a single integrated circuit. In the 6530, they integrated not only the system timer chips, but also ROM, RAM, and peripheral input and output. When you factor in the address decoding logic that would be required and so on, it's quite possible that each 6530 may have reduced, let's say, a dozen regular chips. And so did the 6502 itself. You see, MOS was a chip company, and even when Commodore bought them, Commodore itself was really a calculator company that needed MOS primarily to make chips for its calculators. The people behind MOS, including the brilliant Chuck Peddle, were making a name for themselves with the release of the 6502 processor. The 6502 itself was a prime example of chip integration, and between the 6502 CPU and the two 6530 Riot chips, These three major ICs make up the core of the KIM-1 computer. And that was really their mission back in that day. Take a set of chips that normally appeared together as a board assembly and reduce them to a single IC. After all, the I in IC stands for integrated, and that's exactly what MOS and the KIM-1 were all about. A large number of chips integrated into a single 40-pin packages. It's that level of integration that made it possible to build the KIM and later the PET and the C64 and so on with just a few major ICs. In our first episode, we unboxed the KIM-1 and we even powered it up and wrote a simple machine language program to add two numbers together. We entered that program in hex opcodes using the alphanumeric keypad on the KIM, and we used the LED display for feedback and results. The LEDs and the keypad buttons, rows, and columns are connected to the I/O pins of one of the 6530 chips. Now, we could, in theory, spend our days entering, executing, and reviewing code and results with the keypad and display. And I'm sure some people did that back in the day. But it would get boring in a hurry, I think. There's got to be a better way, and there is. A serial RS-232 connection. To add RS-232, I will be installing a Corsham I/O board that plugs into the expansion connector. Its job will be to adapt the current loop interface that the KIM-1 contains over to a normal RS-232 TTY interface. The Corsham board expects your KIM to be all original, but my board had been modified at some point in the past to provide a simple TTY interface, a reality that will come back to haunt me soon enough. Our little sample program used a CPU to load the original numbers from RAM, added them together using the ALU unit in the CPU, and then stored them back into RAM. But our program did not use or touch the Riot chips in any way. Since my next big goal is to get serial communication working, it's time to learn about the Riot chips in detail. We'll perhaps explore programming the chips in a future installment, but for today, the important part to know is that the KIM-1 contains two of the 6530 Riot chips and why. Each contains 1K of ROM space and a tiny 64 bytes of RAM. It's not a lot, but when combined with just a CPU, is enough to be able to execute rudimentary programs and store the results, like a calculator or an adding machine perhaps. When you have two such chips as we do, you could even use one of the chips' RAM for the heap and one of the other chips' RAM for the stack, and that way they would never collide with one another. If you've done any programming over Arduino or other microcontrollers, then you are likely familiar with the concept of general-purpose I/O pins. In a typical microcontroller, they're generally integrated into the main package, but in most classic desktops, that functionality is actually the responsibility of one or more interface adapter chips, like our Riot chips. The I/O lines are controlled by the two external Riot chips at the behest of the CPU, but not directly by the CPU. Whereas with the much later x86 CPU, you might have in and out instructions. With the 6500 series architecture, it's all done through mapping the Riot chips registers into main memory, so that you can work with them directly that way. Remember that the 6502 has 40 pins on its own, and that's about as big as chips were really getting in the day, so they couldn't actually integrate an additional 32 or even 16 I/O lines, had they even wanted to. Those GPIO lines then are connected to the Riot chip and are controlled by registers located at well-known memory addresses in the system memory map. The CPU does not directly turn off and on its own pins when it wants to do things like controlling a peripheral or communicating over a serial line. Instead, it causes the Riot chips to do that part on its behalf by twiddling their registers directly. Each Riot chip is thus mapped into the system memory space. But what do I really mean by that? Well, each chip has a number of I/O registers that control its timer as well as the direction of each I/O pin and the current value of that pin, whether it's high or low. To access those values, you simply read and write from special memory addresses. All of these special memory addresses are dedicated to the Riot chips, and they appear from 1700 to 2000 hex. That includes their control registers, data direction registers, their RAM, and their ROM. It all lives alongside main memory in the system memory map. Behind the scenes, all the work of making that happen is done by the address decoding logic. There's a set of TTL logic chips that look at the address bus and figure out exactly which chip should be active on the bus for any given memory address in the system memory map. To read a byte of data from RAM, for example, the CPU puts the address of interest on the bus. The system's normal static RAM lives in the range of 0 to 3FF. And when an address in that range is on the address bus, the board's decode logic knows to turn on the chip select lines of all 8 static RAM chips, and they each respond like magic with their lines connected to the data bus, one for each of the 8 bits. The answer then automatically appears on the data bus for the CPU to consume just by virtue of putting the right address on the address bus. To access the first Riot chip, which we said lives up at 1700, the CPU would need to put that address on the bus, so let's say 1703. The decode logic knows that it's not RAM, so they remain quiet and detached from the bus. Instead, when it sees an address in the 1700 to 173F range, it knows it's supposed to live in the first Riot chip, so it activates that chip's chip select line. The Riot chip then looks at the lowest several bits of the address bus to figure out where within the chip the CPU is trying to access. In this case, the third byte into the chip because we looked at 1703. Based on what that address in the chip is supposed to do, the chip does the right thing. If it's a ROM address, it puts the ROM byte on the data bus. If it's a register read, it puts the register's value on the data bus. If it's a write of some kind, it takes the current value from the data bus and stores it in the chip appropriately. The first Riot has its I/O registers placed, as I said, at 1700 to 173FX, and the second chip follows immediately from 1740 through 177F. Right above the I/O areas are two little blocks of 64 bytes each of RAM. Together, they constitute the half page of memory right above the I/O blocks, so from 1780 to 17FF. When you store values in these addresses, the data goes strictly into the Riot chip, and the static RAM is not involved in any way. The little 64-byte bonus blocks of RAM that appear within the Riot chips are completely separate from the main RAM of the system. You interact with them in entirely the same manner, reading to and writing from the memory addresses just like any other RAM bytes. When the address is in the 0 to 3FF range, the address decode logic knew that it had to turn on the chip select lines of the static RAM chips. Hopefully you can see then how the CPU talks to other chips in the system. They simply live at well-known locations in the memory map by virtue of responding when, and only when, their range of addresses is being used on the bus. You might be wondering about the Riot RAM. What's the point of even having 64 bytes of RAM? Well, to be honest, it doesn't make a ton of sense in a computer that also has a kilobyte or more, which is not a lot, but of static RAM. As a programmer, you would likely just use the 1024 bytes of static RAM, not the little 64-byte blocks afforded by the 6530 chips, because there's nothing else special about them. And yet, MOS wasn't primarily interested in desktop computers, at least not yet. They were really targeting the calculator market more than anything else at that time, and so let's say you're building that electronic adding machine back in the 70s. You need lots of I/O lines for the keypad and the LED display, and to control the paper tape advance on the motor, and so on. If you can do it working within 64 bytes of RAM, and if your code will also fit within the 1K of ROM space, then conceivably, you could build your device with just a 6502 and a 6530. No banks of static RAMs, no PROMs or ROMs or anything. It's all integrated directly into the 6530 chip. Now, if you've looked carefully at almost any other Commodore computer, from the CIM-1 to the PET to the VIC-20 or 64, they all have a few things in common, like a 6502-derived processor and two interface chips. In the CIM-1, they're Riot chips, and in the PET, they're called 6520 PIAs or peripheral interface adapters. In the VIC-20, they are 6522 VIAs or versatile interface adapters. For the C64, they were 6526 CIAs or complex interface adapters. The chip numbers would get bumped up, and the name made even more impressive sounding with each revision as more and more functionality was incorporated into the chips. Over the years, the interface adapter chips would gain features like real-time clocks and shift registers, but their fundamental operation would also remain the same. To output values on the Riot pins, you simply set the data direction register to output, and then a bit mask of the value that's being put onto the port. So, for example, you might set the data direction register A to FF, meaning all bits are output. Then you might place 80 as the high bit on the bus. This would have the effect of first saying that you wish to control all of the bits in register A. Remember, there's two, A and B, in each chip, and that you are setting them to output. Then you turn on only the high bit in port A, which will turn off all the output lines except the highest line, line 7, which corresponds to that high bit being set in the hex number 80. Now, if you wanted to read values from the pins, you would set the mask to input, or zeros, and then read the port A register to get the current pin values. Thus, controlling the I/O lines on a CIM-1, PET, or C64 is really quite simple, and they are very powerful in that sense. A few bytes control the entire thing. With a couple of macros, then, you could even replicate the Arduino functionality of digital write and digital read. Now, I was not planning on programming the 6530 directly, at least not immediately. Rather, I plan to connect the Corsham I/O board to the lower expansion connector. That board has the ability of providing a full RS-232 serial port rather than the old-school current loop interface of the raw CIM-1. The only problem is that when I plugged in the Corsham board, I could not communicate with the CIM-1. The additional memory on the board seemed to work well enough. There was just no serial communication. I flailed for a little while, checking things like serial drivers and whether I needed a null modem adapter. Spoiler alert, you don't. The CIM-1 is a little unorthodox in that it expects 2 stop bits, so you wind up running as 8 and 2 as your serial protocol, but beyond that, it's all pretty standard. The most you can likely get away with is 4800 baud, but I was even sticking to 2400 to be safe for now. You're supposed to be able to connect a serial cable and simply press a key on the other end. The CIM-1 will even detect the speed and auto baud. Try as I might, however, I just could not get it to respond. I knew my board had a few modifications in the area of the main 6530 chip, so I got out my trusty magnifying glass for a closer look. Back in the unboxing video, I had already restored 2 components to original. A resistor that had been relocated and a Zener diode was disconnected and lifted. I had fixed those, but it had not yet helped with the serial comms. Fortunately, my KIM-1 came with full schematics, and they're simple enough that even I can follow them. I was quickly reaching the limits of my hardware skills, but I decided to trace the schematic through anyway to see what I could find. And I found something reasonably decisive. In the middle of the terminal circuit was a missing transistor. Q7 wasn't relocated or hooked up wrong, it was gone. A little research into the KIM-1 parts and components list indicated it would have originally been a 2N5371. After some digging around with Google, it seemed that a suitable and available replacement would be the NTE123AP transistor, so I ordered a pack of those from Amazon and waited for their delivery. Can you believe that I had to wait 2 days for an obscure KIM-1 transistor replacement? The supply chain is just affecting everything, I guess. But when they arrived, I checked the board over carefully, and after putting the other components back in place, I couldn't see anything else amiss except for the missing transistor. I carefully soldered in my NT123. My biggest worry at this point was grenading one of the original 3 slate ceramic chips. Damaging any of them would not only seriously harm the value of this KIM-1, it would also mean that I had ruined one of perhaps the last Rev A boards out there with all of its original ICs. I've only ever seen one other, so I really didn't want to damage this one. I need not have worried though. The moment I powered it up with the new transistor, I hurried over to the serial terminal and hit backspace. I was immediately greeted with the KIM-1 monitor prompt. Success. Fast forward a few hours of tinkering and I was ready to load MS Basic into the system. I detailed how I assembled, linked, built, installed, ran, and tested MS Basic 1.0 on this machine from the original source code in the last episode, so be sure to check that out if you've not yet seen it. I knew that the load address for BASIC was supposed to be 2000 hex, but every time I tried to load it, it would crash back into the monitor with an error. I was eventually able to narrow the memory error down to 20FB and 20FC. As soon as those addresses were loaded from paper tape, the system would malfunction or crash. Now that was odd, but it was also suspicious because while 20FC is not an important address in any way, just plain old 00FC is. It's used by the system for internal bookkeeping by the monitor. It gave me a hint, and a little experimentation in the monitor and on the hexpad front panel exposed the problem. 20FC was being treated the same as just plain FC. They were effectively the same address. Everything wrapped around it 1FFF, so that the address 2000 was actually address 0. 2001 was the same as 1, 2002 was the same as 2, and so on. But why was this happening, and how could I fix it? At first, I suspected a bus logic error, something blowing in the address decode section of the board, but in the end it turned out to be both a lot simpler and more complex than that. The thing is, the KIM-1 only shipped with 1K of RAM, and they only needed a few pages of memory space in which to map their Riot chips in addition. They simply didn't need a 64K address space, so they chose to completely ignore the top 3 bits of the address bus. They're not even decoded. The KIM-1 assumes that the top 3 bits are always 0, and that when they are indeed 0, that means something is being referenced down in the 0000 to 1FFF range, which is where all the KIM-1 hardware lives. Those viewers with a little 6502 experience might be wondering how the CPU can boot then, because it normally fetches the startup address from ROM at FFFC. However, if you're just ignoring the top 3 bits, FFFC becomes 1FFC, so that's where the vectors are stored, up in the top of the Riot ROM. When the CPU tries to look up at FFFC, it gets 1FFC instead and finds the right vector that it needs. But how could any of this work with my 60K RAM expansion? Well, it turns out that on the Corsham I/O board, there's a jumper for address decoding. When set to internal, it remains exactly as it was on the KIM-1. But when set to external, that places the responsibility for decoding on, you guessed it, external hardware. In our case, the Corsham RAM board contains the decoding logic for us. To take advantage of it as you crest the 2000 hex address, 2 things are required. First, you must jumper the Corsham I/O board to use external addressing. And second, you must then connect a cable between the I/O and RAM boards. This cable is used to pick up the additional required address lines from the lower expansion connector. Once I did this, fresh RAM was now exposed at 2000 all the way up to DFFF, and there was no more wrapping around or aliasing of addresses. I'll revisit the loading of BASIC briefly in case you missed it in the last episode. I took the paper tape file that we produced from our assembly language build and loaded it into the monitor. Next, I looked at the assembly map file to determine that the program entry point was located at 4065 hex. Then I used the KIM-1 monitor to jump to 4065, which launched MS Basic. The first sign of life is a memory size prompt. You might recall this from early TRS-80 Model 1 computers. It tells BASIC where to put the top of memory so that it knows where to place its own stack and how high free memory actually goes. Most computers, like the later PET, would figure this out on its own or hardcode the answer into BASIC, but the KIM-1 just asks the user. Next, you were asked your terminal width, and I responded with 80 since that's how my console window is set up that I'm using. Finally, you were asked if you wish to have the trigonometry functions like sine and cosine available to you at the cost of extra memory. I answered in the affirmative and then wrote a simple BASIC program to animate a little drawing in a smooth sine wave arc. With that, we now have a fully operational KIM-1 that we can communicate with, program, and upload and download to from at will. This will enable my exploration of the rest of the KIM hardware, including the visual memory board, the dual memory expansion boards, the disk controller, the PROM burner, and much more. As promised, as long as there's sustained interest in the KIM-1 series, I'll keep diving deeper and deeper into it. All I need from you are the views and likes and subscribes to show me if there actually is interest, and I'll just keep plowing away. So if you enjoy this type of thing, let me know by leaving a like, and let the algorithm know by doing the same thing. If you are a new viewer of my channel who'd like to see more like this, please let me know by subscribing to the channel. If you have any interest in matters related to autism, Asperger's, or ASD, please check out my book on Amazon, Secrets of the Autistic Millionaire. It's got nothing to do with money and everything to do with living a successful life on the spectrum. It's everything I know now that I wish I'd known back then. Now remember, I'm just in this for the subs and likes, so please be sure to leave me one of each before you go today. In the meantime, and in between time, I hope to see you next time, right here in Dave's Garage.
Do it, Glenn! Do it! Do it!